Here's an old exam question about electrodynamics. You should pause the movie, download the question from the link below, try it yourself, and then resume. And don't forget while you're at it to like and to subscribe, and sometime go and visit my website www.learnscience.co.za. There you can find a lot of resources easily categorized so that you can find what you need. Here we're given a diagram and we need to decide what it is. Clearly, it is a generator rather than a motor. Click that link to remind yourself of the difference between the two. But quickly, we can see that because there isn't an external power source like a battery or an alternating current source. This is the power source. This is going to generate electrical energy from the inputted mechanical energy. We can see the sign means that we are inputting motion. So something will have to rotate this armature. By doing so, somehow electrical energy is generated. You can't just take an armature and rotate it and expect that electrical energy will be generated. We need to have a magnetic field, and we need to have something that experiences a change in magnetic field. Not any old something, a conductor, the armature. We see that we do have a magnetic field between the north and the south pole of these two permanent magnets, and the armature sits inside that magnetic field. Just being inside the magnetic field is insufficient. The wires in the armature need to experience a change in magnetic flux. And only when they experience a change in magnetic flux can current be induced in the armature. How do they experience a change in magnetic flux? The armature needs to be rotated. Why should that cause a change in magnetic flux? Between these magnetic poles, you can imagine there being field lines. We can also call field lines magnetic lines of flux. This armature consists of a coil of wire, and as that coil rotates, can you visualize how the arms of the coil cut through these magnetic field lines? And by them cutting through the field lines, they are experiencing changing magnetic flux. And when a conductor experiences changing magnetic flux, an EMF is induced across it, which drives current to flow through it. And that we call electromagnetic induction. For more about electromagnetic induction, click there. But still, we haven't really discussed what this is. Yes, it's a generator. It's not a motor. But what kind of generator? Is it an alternating current generator or a direct current generator, AC or DC? First of all, what does that mean? This generator, as I've explained, is going to generate electrical energy. And that electrical energy is then going to be transmitted to the external circuit. So the question is really asking about the nature of that current that will flow in the external circuit. Will it be continually in one direction in the external circuit, DC, direct current, or will it flow back and forth in direction, alternating current, AC, in that external circuit? How do we decide which one it is? We look at the connection between the armature and the external circuit, and we see that it is a split ring commutator, not a slip ring commutator. And the fact that it's a split ring commutator tells us that this is a DC, direct current generator. Why? I know the question's not asking that, but let's use it as an opportunity to improve our understanding of this topic. Inside the armature, the rotation causes current to be generated, or we could say an EMF to be generated. The EMF generated and the current generated are directly related because the EMF generated causes the current. So I might use those interchangeably and understand, in this case, if I say one is increasing, the other is also increasing. The EMF that is generated by this rotation, whether it be in an AC or a DC generator, is generated in such a manner that within the armature, it changes direction every half revolution. Now the split ring commutator swaps the brush that it is connecting each armature arm to every half revolution. And in so doing, that split ring protects the external circuit from the armature's changes in direction of current every half revolution. That's why a split ring commutator allows there to be a direct current in the external circuit, DC generator. But now, the split ring cannot protect the external circuit from the changes in strength of the current induced in the armature. It does protect the external circuit from the changes in direction, but not in strength. Let's go back to what happens during electromagnetic induction. Remember that in order for an EMF to be induced, the wires in the armature have to cut through magnetic lines of flux. They need to experience change in magnetic flux. We have these magnetic flux lines between the north and the south of this magnet. And here we have the armature. Let's imagine that this coil is positioned this way. And when positioned this way, can you see that the rotation of a certain amount of the armature causes the armature coils to actually move parallel to the magnetic flux lines. And so for a little while, there is no cutting of flux lines while the armature rotates this little bit. Then, if we come to the other extreme in this explanation, if we have the armature cutting the lines perpendicularly like this, then in the same amount of time as just now we saw no cutting of lines, now we get quite a lot of cutting of lines. This is the most efficient for cutting lines. We can think of cutting bread to help us to understand this. If we have a loaf of bread on a breadboard and we cut at a certain rate, if we're going to cut skew, then we won't reach the breadboard as quickly as if we cut perpendicularly, because cutting skew kind of like wastes some of our effectiveness. In a similar way, we have these two extremes, that when the armature is cutting the magnetic field lines perpendicularly, then it is cutting most lines per second possible. And that induces the strongest EMF possible for that setup. At the other extreme, when the armature is moving parallel to the field lines, then no magnetic field lines are cut, and so there is no EMF induced. And in between those two extremes, then it's like cutting the bread skew, obliquely, and then we get something in between. Let's discuss the EMF changes that occur during one full revolution of the armature. Of course, we could start our explanation and our graph that we're going to draw at the same time at any point within the rotation, but let's choose this point. So I'm representing one arm of the armature with this hand and the other with that one. And we're going to do a full rotation, and you will recognize that is a full rotation by the hand that was at the top coming back to the top. That will be a full rotation. We start off at the instant when the armature, in effect, is moving parallel to the magnetic field lines, and so the induced EMF is 0 volt. And then that increases as the obliqueness turns into a perpendicular cutting at this point. Maximum EMF at this point, and then decreases down to 0, where we get parallel motion relative to the magnetic field lines, increase up to maximum here at this perpendicular cutting point, decrease to 0. Just make sure that you also label the axes appropriately. The y-axis in this case is the induced EMF in volts. Now in this particular question we were asked to draw a graph of the EMF induced over time. So we know that the x-axis should be time. If we hadn't been told that, it wouldn't have been wrong to say angle of rotation on the x-axis. And before we go, have you already liked? Have you subscribed? Have you left me a comment? And please go and visit my website. You'll find a lot of resources there, and they're categorized in a way that will make it very easy for you to find what you need. Until we meet again, learn science!